My name is Andrew Zheng, and I'll be presenting on Mora, an algorithm that does abundance-aware metagenomic read reassignment for disentangling similar strains. Taxonomic classification is mainly used in the field of metagenomics as a precursor step to understanding microbial communities. However, most algorithms currently only have high precision at the species or genus level. We introduced Mora, an algorithm that also has high precision at the strain level, by maximizing the alignment scores between the unknown reads and the reference genomes, while also trying to minimize the difference between the final abundances and the estimated abundances. Here, we first look at the overall pipeline of Mora. Given some unknown reads and some reference genomes, an initial alignment algorithm, such as Bowtie2 or Minimap2, is used to output a SAM or a BAM file. This file is then fed into Mora to calculate the estimated abundance levels by use of these two algorithms, which are heavily inspired by ISMB. Once the estimated abundance levels are calculated, it is fed into our reassignment algorithm to output our final results. We now explain how the reassignment algorithm works. It is modeled as a non-linear optimization problem called the Weapon Target Assignment Problem, or WTA. In the WTA model, we heavily punish over-assigning reads to a common reference genome. This is so that we can find the less abundant references. For example, we have 4 reads shown here, differentiated by their color. And we have one unknown read here that we want to assign. However, in R4 and R2, we have no more space left, and we don't want to over-assign reads to a reference. To fix this problem, we try to open up space. So we move this read from R2 to R3 so that we can assign this unknown read to R2. When trying to compare Mora and other algorithms, we mainly look at Pathoscope2 as it is used a lot in many literatures. However, Pathoscope2 had a problem with outputting results, so we had to change a bit of the code and relabel it as argpatho2 in the following figures. We first looked at how well Mora and argpatho2 worked on E. coli reads of different strains. Shown in red here are the 3 dots representing the real abundance levels of our unknown reads. And as we can see, Mora assigns most reads to these 3 correct strains, while argpatho2 assigns a lot of reads to this incorrect strain, and Bowtie2 assigns reads almost equally across all strains. In a similar experiment, we looked at how well Mora and argpatho2 worked on long reads that only differ at the strain level. Running Mora and argpatho2 with Minimap2 as the initial aligner on COVID reads, we see that all 3 algorithms assign the most reads to the alpha strain, as these COVID samples were obtained from the US in 2021, during which the alpha strain was most prevalent. We can maybe say that Mora was most likely to be correct in this experiment. We also looked at how well Mora compares on diverse reads. And using simulated data, we looked at 2 cases. When we have a good guess of where the genome or where the reads come from, ref1 with 400 genomes, and when there's no information at all, which is ref2 with 6,487 genomes. Looking at wall clock time and RAM usage, we can see that Mora outperforms argpatho2 in all cases except for RAM usage when assigning short reads to ref1 and to ref2. However, in terms of time, Mora is 20 to 50 times faster in all cases. Looking at the score comparison, which is the F1 score, we can see that Mora is oftentimes slightly better than OGPATHR2, or a lot better or comparable. It is only on short reads to ref1 at these different taxonomic levels does OGPATHR2 have a higher F1 score compared to Mora. In conclusion, we see that Mora performs comparably well to OGPATHR2 on diverse reads. However, Mora has much shorter runtime and uses less RAM. This difference is even more when looking at reads at the strain level, where, as we saw, Mora outcompetes OGPATHR2 and the initial liners by a lot. As we recall, the pipeline of Mora is also quite modular, so Mora can be easily incorporated into any metagenomics pipeline as needed. Hence, we believe that Mora can be a very useful tool to scientists that are looking at strain level comparisons. Thank you very much.